Welcome to ilectureonline. In order to get a better understanding of transfer functions, let's do an analysis of our simple transfer function for this simple circuit where we have a source voltage, a resistor, and a capacitor with the output voltage across the capacitor. Now notice that this was the transfer function starting at 1 for a frequency equal to 0 because at 0 frequency, of course, capacitor offers no current flow, therefore the entire voltage across the output is the same as the voltage across the input, and as the frequency increases, it transfers into what we call a short circuit, and therefore, of course, the impedance across the capacitor decreases and the transfer function goes eventually to 0 as omega goes to infinity. Remember the definitions of the magnitude of the transfer function and the phase angle of the transfer function. Here, let's take a look at a table with some values. We have what we call the frequency. We have the ratio of the frequency over frequency sub naught, where frequency sub naught is equal to 1 over RC. It's basically the inverse of the time constant. Here we have the magnitude of the transfer function and the phase angle of the transfer function. You can see that when omega is equal to 0, which means a steady state current, the ratio is going to be 0, and the transfer function is going to be equal to 1. In other words, the output voltage equals the input voltage, and the phase angle is going to be equal to 0 degrees. They are in phase. The output voltage will be in phase with the input voltage. Notice as then the frequency increases and becomes equal to omega sub naught, which is the inverse of the time constant, the ratio will then equal 1. The magnitude will be 1 over the square root of 2, which is 0.707. That's a special point right here. And then you can see that the phase angle will be minus 45 degrees, that the reactance of the capacitor will then be equal to the resistance of the resistor. So the impedance phase angle at that point will be 45 degrees. When we increase the frequency of the source to twice omega sub naught, then notice the ratio is 2. The magnitude of the transfer function now drops to 1 over the square root of 5. That comes out of this equation right here, which is a little bit less than 0.5, with now a phase angle of 63 or minus 63 degrees. When we go to 5 times omega sub naught, so the magnitude or the ratio is 5 to 1, the magnitude of the transfer function now drops to 1 over the square root of 26, which is slightly less than 0.2 with a phase angle of minus 79 degrees. And of course, in the limit, as the frequency approaches infinity, the ratio will go to infinity, the transfer function then will go to 0, and the phase angle will then approach minus 90 degrees. So hopefully, again, this will help you understand what transfer functions are and what it looks like in this particular case with a capacitor and resistor in the circuit connected to a time-varying or a frequency-varying voltage source. And that is how we understand what a transfer function is.